So my name is Justin Pena. Today I will be presenting my senior thesis of 3-trimethylsilyl-purpagel amino acids via reductive amination. There we go. The goal of the project was to synthesize in high yield N-purpagel amino acids via reductive amination. This is a continuation on previous work done on N-purpagel amino esters as shown in the top figure. I was given basically the task to use this similar reaction and to tweak the conditions to accommodate for a free amino acid. In order to do this, I delved into the literature that was used for this previous project to understand the conditions of each of the reactions throughout the literature, the primary reactions that are used throughout the literature, and the reasons why amino acids are so sensitive. And by using that, I would be able to try to circumnavigate this problem or circumnavigate the problem of having the amino acid unprotected and thereby accommodate it in a reductive amination or some kind of other reaction if possible. Okay, let's see. Introduction and background. N-purpagel amino acids are of interest due to their building block potentialities in materials such as beta peptoids and nitrogenous quaternary cyclic rings. The first conclusion that I came out through the entire literature, unfortunately, was that most of these reactions, actually not most of them, almost all of them used a protecting group because the amino acid was so sensitive. And the reason why amino acids are so sensitive in any conditions has to do with the fact that they lack compatibility in organic solvents, and they, due to its Switter ionic nature, is sensitive to changes in pH, which reductive amination usually uses a basic workup, so that would be a problem because of competing side reactions for the C and N terminus. As shown right here in the blue, C terminus, N terminus, and I sort of put this figure on the slide to just show the difference between an amino ester and an amino acid and just like a basic interconversion. What's next? So, upon reading the literature, 3 primary reactions are shown for the N-purpagylation of amino esters in general. Literature showed reaction A, base-activated SN2 alkylation, shown right here. I don't know. Yeah, you can see the arrow. Good. Okay. B, reductive amination via interception of an amino intermediate with an allelic nucleophile is shown right here. And C, reductive amination with the purpagel aldehyde. SN2 of base-activated alkylation works on the basic premise of deprotonation of the N-terminus of an amino ester. That now created nucleophile will attack a electrophilic purpagel halide, thereby causing substitution and forming the desired N-purpagel amino ester product. B, reductive amination via interception of an amino intermediate by an allylic nucleophile. This works through a slightly acidic workup where the purpagel aldehyde is activated and then attacked by the N-terminus right here to form in a medium intermediate. This is then intercepted by an allylic nucleophile shown right here, and then the arrows show the subsequent transformation in the green. And then C, reductive amination with a purpagel aldehyde. Oh shoot, I forgot the base, but that's okay. This generally works in a mild basic condition that activates this N-terminus, which makes it nucleophilic and ready to attack a purpagel aldehyde, which is electrophilic in nature. This forms a Schiff-based amino intermediate, as shown right here. This is the Schiff-based intermediate, and then it is subsequently reduced by reducing agents such as sodium borohydride to yield the N-purpagel amino ester, or in my case, what I desired, the N-purpagel amino acid. Reactions A and B were undesirable for a multitude of reasons for amino acids specifically, because, for example, reaction A used much harsher basic conditions to activate the nucleophile. This would in turn cause competitive side reactions through the possible deprotonation of the carboxylic acid moiety on the C terminus, which is not desirable because we want the N terminus to do the addition. B, reductive amination via an allelic nucleophile intermediate won't work because this procedure is just not adaptable to either an amino ester or an amino acid, because it produces 2 additions, so there's no way to increase this, to allow this for cross-compatibility. Reductive amination, therefore, would be in favor for both because it uses mild basic conditions to promote this addition, which therefore would have less of an effect on the Switter ion character of an amino acid. Yes. Okay, why is this project specifically of interest? Well, not only for the pharmaceutical building blocks, but the reason why we wanted to do this was to have to eliminate the later needed step of deep protection. This would make it more efficient and also it would allow us to not waste more of our product. So the overall idea of our group is to green our syntheses for future applications. Results, what to expect. So the 2 amino acids that I tried to propagulate were glycine and valine. Right here is a chem-draw generated HNMR of the expected peaks for N-propagulated glycine. As you can see here, there should be a singlet peak at 13, a singlet peak at 3.49, a singlet peak at 3.32, a singlet peak at 3.29, and a tall singlet peak involving all these same methyl groups coming off the silicone. However, what actually happened was the reaction did not proceed to completion, and this right here is a chem-draw generated HNMR of glycine, and as you can see here, you'd expect to see a peak at 13 ppm, a singlet peak for nitrogen at 8.7, a singlet point peak at 4.02. And the reasons that I came up with for this possibly failing had to do probably with either the stoichiometric amounts or pH. I first explored stoichiometric amounts by tweaking this in my reactions, but to my dismay, that did not work at all. So I attempted to look in the literature for pH controls for selective addition of the N-terminus. Unfortunately, I did not find anything that would help me. I found things that were optimally selected for the N-terminus of peptides, but no amino acids. However, in the last in the recent weeks, I found a paper that is of great interest that will, I think, circumnavigate this problem and finally bring this issue to resolution. This paper is a new methodology that uses reactants renewed out of renewable feedstocks. These renewable feedstocks are created out of things like fermentation of lignocellulose to make the alcohols, and then for other renewable feedstocks and atmospheric nitrogen to produce natural amino acids. And then, they used invaluable iron catalysts and then the hydrogen borrowing method. This right here is a concept map from the paper itself. I took it directly off the paper itself. It sort of shows the overall premise of what they're trying to get. They want to basically create a pathway for overall renewable feedstocks and resources to make the whole process for the building blocks for pharmaceuticals and other biologically interesting compounds by just starting from the ground up. So right here is the energy-intensive and non-renewable Haber-Bosch process, and then this is their proposed process with using atmospheric nitrogen and renewable sources to produce amino acids and alcohols, which are then coupled to release only water as a byproduct and produce N-alkylated amino acids. How do they do this? With the hydrogen borrowing method. A hydrogen borrowing method uses a catalyst to oxidize an alkyl alcohol to produce a carbonyl intermediate, which is then coupled in neat conditions with a free amino acid to release water and form an ammonium intermediate. Then this catalyst will release the hydrogen, subsequently reducing the ammonium intermediate to form the desired alkylated product. They were able to do this with stereochemical purity, and they were able to do this. They were able to do this selectively, either by monoalkylating it and dialkylating, depending on the catalyst used. Also, they were able to do this without protecting polar side chains. If you are interested, this is the catalyst they use for monoalkylation tricarbonyl pentadione iron 3. And this is my proposed scheme for attempting to apply this to propargylation. I think because the alkene group is protected by that silicone end of the propargyl group, this will be able to be cross-compatible. Subsequent oxidation will occur on the a propargyl alcohol, making a propargyl aldehyde, which will then be coupled in neat conditions with an amino acid, releasing water, forming an amine intermediate, and then subsequent reduction will occur, forming the desired N-propagyl amino acid product in relatively neat and environmentally friendly conditions without the need of a protected group. Future work. So I decided to do a proposal or future work on the dipropargylation of lysine. So basically monopropargylizing this group right here off the N-terminus, and then the lysine residue as well. Oh, well, that's kind of repetitive, isn't it? Okay, well, we'll just skip that slide. And this is my proposed modified scheme for future work. So the plan would be to first propargylate the N-terminus, and my mindset being there that it would be protected and thereby wouldn't react again if I tried to run this through another cycle of this, where the N-terminus would be, or not the N-terminus, the side chain would be propargylated and the same process would occur to yield the desired product. This is my references, and any questions? Sure, yeah.
Did you, when you're doing the reaction, did you TLC to see if you're getting unique information at all?
No, I didn't. I was instructed to use H NMRs to see if I was forming any product in the crude form, and there really wasn't much to be formed at all. So I just kept trying to troubleshoot it.
In any of those troubleshoots, did you try a different reducing agent?
Yeah, I switched to sodium borohydride over sodium borohydride, and that didn't really change anything either. Yes, Alex?
With that catalyst, is that the one that you proposed, would that be susceptible to more acidic environments, especially if you're looking at something like a bitter ion?
I don't think so. They relatively ran this in neat conditions, so it kind of bypassed that problem a little bit. Either that or they used like a mild amount of solvent to be like pretty efficient. So I don't think it would be a problem, but obviously I would have to like bring it into lab and do more rating to determine that for myself. But it seemed like a good future like stepping point.